In this video, we'll be learning about the distance of a point from a plane. So when we're talking about the distance of the point, we can consider any distance. But when we say distance, we always mean the shortest distance from the point to the plane. The shortest distance here is going to be the perpendicular distance from the point to the plane. So let us consider the point A, and let's say the point A is having a position vector B. Okay. So this is the point A, and the point A is having the position vector V. And let us consider the plane. So this is a given plane. So here we need to find what is the distance between the point A and this plane. So to do that, what we do here is consider another plane which is parallel to this plane, but passing through this particular given point. Yeah, this plane is parallel to the given plane, but passing through the point. Now, if we find the distance between these two planes, that is the distance between this point and this plane. Okay. So now what we'll do is we'll consider another arbitrary point R on this given plane. Okay, and let the position vector of R be W. Yeah. So we have fixed the point A, but the point R is arbitrary. Okay. So now by varying a particular parameter, we can generate all the points in this particular plane. That's why we consider R to be the arbitrary point. Now let us consider the vector which is connecting the point A and R, the fixed point and the arbitrary point. We call it to be AR. Then from the vector addition, we know that OA vector, where O is the origin, OA vector plus AR vector is equal to OR vector, right? So now what we'll do is, we'll express AR in terms of the position vector of this point R and point A. So AR is going to be OR vector minus OA vector. And now if you see this particular vector, that is AR vector, is lying on this particular plane, right? So this is lying on this particular plane. We will be considering the unit vector which is perpendicular to this particular plane. So since this vector is perpendicular to this plane, then this vector is perpendicular to this vector also. So their dot product will be equal to 0. So we will be using this as one of the key to find out the value of the distance. So let's just start whatever we have till now. So now I've tried to draw the same thing in the board over here. So we have the plane pi1 which is given and the point A which is given. So let's say the equation of the plane pi1 is r vector times n cap vector is equal to d. The n cap vector will be same for both the planes because they are parallel, right? So r vector here is position vector of some random point in this particular plane, right? And d is a distance, perpendicular distance from the origin to this particular plane. So this part is what we learned in the starting in GeoGebra. So we know that this RA vector is equal to OR vector minus OA vector, right? So now what we do is, we know that OR vector is R vector and OA vector is A vector. So RA vector is going to be equal to R vector minus A vector. And one more thing here is, if n vector is n vector is a unit vector for both these planes. So we know that n vector is unit vector of this also. That means n vector is going to be perpendicular to this also. If n vector is perpendicular to this plane pi2, then it will be perpendicular to the vector which is lying on the same plane. So since n vector is perpendicular to r vector minus a vector, their dot product is going to be equal to 0. That is, r vector minus a vector dotted with n vector is equal to 0. So performing the dot inside, we have r dot n vector minus a vector dot, sorry, this is n hat vector, n hat vector is equal to 0. So we have r vector dot n hat vector is equal to a vector dot n hat vector. But look, for every plane, this is going to be the equation of the plane, right? So if this is the equation of this r vector is some arbitrary point in the plane pi 2. So that means this is going to be the vector form for the equation of this particular plane. But my right hand side is going to imply the distance from the origin. That means this is going to be the perpendicular distance of the plane pi 2 from the origin. Right, from comparing the actual vector form of the equation, we can see that this a vector dot n vector, let's take the modulus because we want the distance to be positive. This is the perpendicular distance from origin to the plane in which the given point is considered, that is pi 2. So we just saw the original plane which was given. The perpendicular distance from the origin to that plane is d. So this entire thing is d. And we just now derived that the perpendicular distance from the origin to the plane in which A is considered is A vector dot n hat vector. So what is the distance between this plane and this plane going to be? So it's going to be the entire distance from origin to this plane minus the distance from the origin to this plane. That is d minus a vector dot n hat vector. So that means the perpendicular distance between this plane and this plane is going to be d minus a vector dot n hat vector. Right. So what I have done is I've just considered another point B on the first plane, that is a given plane, and that point is a foot of the perpendicular of the line drawn from A to this particular line. So that is nothing but the perpendicular distance between these two planes, that is the shortest distance. So let's call AB is going to be equal to d minus a vector dot n hat vector. Since this is the distance I want it to be positive, so we'll have AB is equal to modulus of d minus a vector dot n hat vector. But we can't always expect that we will be getting the unit vector, right? So we might get a vector which is normal but need not be unit. So in that case, the equation of the plane might be looking something like this: r vector dotted with just some random n vector, not n hat vector, that is equal to some random d. So in this case, I would like to use this particular formula. I would like to reduce this equation in terms of unit vector. So to convert this vector into a unit vector, since this is already a normal vector, to convert it into a unit vector, we just have to divide it by the modulus of this particular vector. So if we are dividing it by modulus of n vector this side, we have to divide it the other side also. So we are going to have it as r vector times n hat vector modulus of n vector, that is equal to d by modulus of n vector. Substituting this value over here, we have AB is equal to d by, so in place of d, we have d by n vector minus, in place of n hat vector, we have this a vector dot n vector upon magnitude of n, or we could just simply write it as d minus a vector dot n vector, the whole upon magnitude of n vector. So the main thing you have to see is here this is a unit vector which is perpendicular to the plane. If you're not given with a unit vector which is perpendicular to the plane, if you're just given with a vector which is perpendicular but not a unit vector, you could use this particular form. So both of this is in terms of vectors. So this is nothing but vector form of the equation. Now let us look at a special case where the point is not there somewhere in the space, it's there in the origin itself. Yeah, the point A is in the origin itself. That means my A vector is equal to 0 vector. So what happens to my perpendicular distance from the point to the plane? My AB is going to be, that is some point which is perpendicular, lying in the foot of the perpendicular drawn from A to the plane, is the AB is going to be equal to d minus 0 vector dotted with n vector, the whole upon magnitude of n vector. But any vector dotted with 0 vector is again 0. So we have AB is equal to d upon magnitude of n vector. So this is the perpendicular distance from the origin to the plane.